In section 5.3, we took half a page to calculate this definite integral. Go back and look at that video if you don't believe me, right? So now I want to use the fundamental theorem of calculus part 2 to integrate this super quick. So that says integral from a to b of little f of x dx equals capital F of b minus capital F of a, where capital F is the antiderivative of little f. Okay, so if I take the derivative of capital F, I get the function. So all I need to do, what this is saying is all I need to do is find the antiderivative of little f here. So let's integrate little f. And then we evaluate at the limits of integration. So if I integrate little f, all right, what does that look like? The integration x squared plus 1 dx. I add 1 to the exponent. So I get add 1 to the exponent, divide by it. And then I add 1 to the exponent. Right now, x to the 0 is equal to 1, right? So I add 1 to the exponent, and then I divide by it, and then I plus c. So all of my antiderivatives are in the general form. Capital F of x equals x cubed divided by 3 plus x plus c. Okay, so I input some x. Now, take the example that we have here and apply the fundamental theorem of calculus. We have f of b minus f of a, so f of 3 minus f of 0. And so now I'm going to plug a 3 in everywhere I see an x. And so I have 3 cubed over 3 plus c minus f of 0 cubed over 3 plus 0 plus c. Simplify this, I get 9 plus 3 plus c minus, so I put a minus on everything in here. Now that's 0. 0 divided by 3 is 0, right? And then that's 0, so that's another minus 0. And then that's a minus c right there. So what do I notice? The c's cancel. No matter what c you pick for your constant of integration, whenever you calculate f of b minus f of a, they always cancel out. Okay, so that's kind of a cool fact there. We don't ever have to write out this constant of integration whenever we're calculating, when we're using the fundamental theorem of calculus part 2, because the c's end up always canceling each other. Just giving you a particular solution. If you picked f of x equal to x cubed plus 3 plus, or divided by 3 plus x plus 2, if you put a 2 in here, what would happen? Those 2's would end up canceling each other just the same. So what we're basically doing is we're just basically choosing to add 0 for our constant here, and we're only looking at this part right here and evaluating, okay? So when I simplify, I get 3 plus 9 gets me 12. Now, let's do this the fast way, like what I was just trying to explain. So I take integral from a to b, f of x dx, and so I do my integration. So I integrate, and I just choose the clever c equal to 0 here. And so because I do that, I don't have to worry about it, because in the end, the constants cancel anyway, no matter what c is, so we might as well not worry about it. And so how do I write this to be quicker? I do this vertical bar, which means to evaluate it at f of b minus f of a here. So this is my b term, and this is my a term here, okay? So I put that vertical bar there. That's the standard notation there. Sometimes I see people, textbooks, they do it like this. So if you want to do it like this, that's perfectly fine. If you want to, I've seen some people do it like this. I'm a little hesitant about doing it like this because, I mean, are you talking about just x? Are you talking about all of this? You know, so the parentheses for sure tells me, hey, look, they're talking about plugging in 3 into every x in this parentheses here. Okay, so either one of those notations I'm cool with. If you want to drop the vertical bar, then do the bracket stuff like that. Okay? So this is, once again, I just plug in the 3, f of b, which is f of 3 minus f of a, just like this, and then I get 12. So I'm telling you, like, this way is the fastest way. This is how I would expect you to do this type of problem right here.